The search space of a CSP can be huge, and therefore to prove satisfiability there is a massive imperative to develop algorithms and techniques to reduce the search space and therefore find solutions faster. At Glasgow University, I learned how an arc is defined as the relationship between their variables and their constraints. This results in a bipartite graph with the variables on one side and their constraints on the other, the edges in the graph representing the arcs. We will now review arc consistency to understand how we can make this better.
Arc consistency. Here is a sample CSP with the variables A, B, C, D, and the constraints numbered on the top left. As we progress through the algorithm for arc consistency, we can see the domains getting reduced and the arcs getting dequeued and queued again. Finally, the algorithm terminates when the queue is empty, and we can see here how the domains of the variables have been reduced. However, the issue I'd like to highlight here is that we have added the same arcs to the queue multiple times. By introducing an ordering to our variable, we can then consider arc consistency only in the direction induced by the ordering. With the ordering A to B to C to D, we can now use directional arc consistency. First, we consider the highest element in the ordering, variable D, which is related to variable C. We'll now prune all the values in the domain of C which don't satisfy constraint 3. Moving down the ordering, we get to variable C, which is related to variable A. We will again prune all values in the domain of A which do not satisfy constraint 2. And finally, we consider variable B, which is again related to variable E, pruning all values in variable A which don't satisfy constraint number 1. The result of this is directionally arc consistent, but not fully arc consistent. For example, if we choose value of 1 for variable D, we cannot get a value in variable C which satisfies the constraint. But it is directionally arc consistent. Going from lowest to highest, we can see now that variable A is arc consistent with respect to variable B and to variable C. And variable C is arc consistent with respect to D. Directional arc consistency theory. We already have a notion of arc consistency among nodes in a constraint graph. And as I have shown, for directional arc consistency, we need only consider arc consistency in one direction. Directional arc consistency makes the node on the graph J arc consistent with respect to I, but there is no need to make I arc consistent with respect to J. For it is the order of the nodes which gives rise to the notion of directional consistency. We only need to prune values in the domain of J and not in the domain of I, as the order in which we process nodes is already defined. That is, a value is assigned to I only after a value is assigned to J. And since J is already arc consistent with respect to I, a value for I can always be found. The result of this is that the amount of work is reduced by half, as only one direction is consistent. And that once a node's domain is pruned, it doesn't need to be pruned again. So we have explored directional arc consistency as a means to reduce the domains of variables with respect to an ordering. Directional local consistency is the term used to describe arc consistency, path consistency, and I consistency with respect to an ordering. It's directional, as in the ordering of the variables, and locally consistent, as in the degree of consistency which is to be forced. The thesis behind these methodologies is that past variables should be consistent with future variables in that ordering. To understand how we get to an ordering, let's first look at an ordered graph. The width of a vertex in an ordered graph is the number of its earlier nodes. In other words, how many parents does a node have? In this example, node D has 1, node C 1, node B 1, and A has no parent. To get this ordering, there are greedy algorithms such as min-width, which can be used. But what this all for? There's some nice properties that arise from this, such as for directional arc consistency. If it's an ordered graph of width 1, that is, it's a tree, then a backtrack-free search can be guaranteed. The same is true for directional path consistency, wherein that if the induced width of the resultant graph, again, the number of parents, is less than or equal to 2, then backtrack-free search is also guaranteed. And this is important. Backtrack-free means that while a solver is traversing down the tree that is the solution space, once a value for a variable is chosen, that choice is never unmade due to a dead end reached further down the tree, thereby making the solving of CSP faster. Hope you have enjoyed my presentation on directional arc consistency. Thank you so much for watching.